So you've been working on a Swift app?
Yeah, I started writing my first Swift app.
What are
I
you
have no
doing it
idea
for?
I have no idea what I'm doing. I'm just following tutorials and I'm copying and pasting code online, and I'm getting angry because I'm reading a tutorial and there's just like it's like your first Swift app, and then there's just so many assumptions they make. Like I know
Are you
nothing. I just know nothing about anything. So
are
yeah.
you using AI?
No, actually, I to be fair, this is my second Swift app, so maybe the problem is me because I did. Apple has this ML Stable Diffusion app, which is uh, Stable Diffusion in Swift, and so I was able to take that and tweak it. That was about I don't know, probably like a year ago.
Oh, cool.
But I'm doing like a fresh app, like something that I'm creating. I'm writing like a little randomizer, so it generates a random number, which sounds really simple, but there's a whole bunch of like I guess like set some context. Uh, when you play online poker, which I
I was
play
about
a
to
lot
say.
of,
I was about to say, is this for poker? I knew it
yes,
was. I wish I had said that before you said something because I knew it
uh,
was about poker.
you have to you have to randomize in a lot of spots. Like there's a lot of spots you just have to randomize in. You're basically like you're indifferent. Your actions are indifferent. So whether you call or fold, if someone's bluffing, like whether you call or fold, it doesn't matter. They both make the same amount of money.
There's
So you don't
situations where your EV is the same.
exactly. So you don't want to always call because then that can be exploited. Because then people just and you
Mm.
don't want to always fold because then that can be exploited. So in these spots where you have very close to the same outcome, you need to randomize. So a lot of people like they go to like Google and you can tell Google to like generate a random number between 1 and 100, and it actually like Google brings up this custom Google UI that's like
Oh,
a random
cool.
number. It's really cool, yeah. Uh, anyway, when you have a bunch of windows and I'm playing on the laptop, like that thing gets lost. So my Swift app idea is a menu bar app, which is really cool. Like they have like a whole thing for just creating a menu bar app. And then I can just click it and generate random numbers. And then I can do things too. Like there's like a lot of times where it's like, you know, when you look at like the way that solvers play, they're like, oh, 17% of the time I'm going to do this, and 6% of the time I'm going to do this, and blah, blah, blah. But humans can't. That's like way too complex for humans. So humans, it's like, yeah, 50-50, 70-30. So I'm going to like do like some color. The thing I'm trying to get working now is like some color coding. So like if it's 0 to 30, it's going to be green. If it's 30 to 60, it's going to be yellow. It's really like 0 to 33,
Mm-hmm.
34 to 66. Anyway, all that to say that, yeah, Swift is, again, I have no idea what I'm doing. One thing I really appreciate, I'll just wrap up on this, is Xcode is like, I don't know, I kind of like live in VS Code and live in Vim, and Xcode's pretty cool. Like when you start the app, you just immediately get that. You get like your code on the left and your app on the right. And so you're like making changes and you're just seeing your app update. And it's like, yeah, we don't have that with like we're
Yeah.
like alt tabbing and all this, hot module refresh and reloading and so yeah, thought that was pretty cool.
Even with it's like a menu bar app that's in the previewer, or like a native, like the whole
No, it's like
UI.
it's a native
Gotcha.
app. So that's one of the things I have to do is like I actually found the tutorial for this part, but you like basically disable the native app. And there's like a setting in your config where you can get it out of the dock. But I think I want to do something. You know how like with tuple you can like click the thing and it pops out this like custom UI. I want to like just see what that's like.
Mm-hmm.
Um, and like even if I did like a web view or whatever.
Yeah.
But yeah, I just want
Do
to.
you want the color? I was gonna ask, like, if you look at the title bar, will the actual icon show the color so you don't even have to click on anything to know what your move should be, or do you want to click on it and see some more details, or both?
Um, I want to click on it to generate the number. There are ways you can like have the number generate every 30 seconds or whatever, but
Mm-hmm.
that's just noisy. So I just want
Yeah.
to click it to generate the
Yep.
number. I don't know. I was thinking of it's like side project, right? You like start something simple and then you're like, oh, I have 50,000 ideas I want to add
Yeah.
to this. So,
Yeah.
but yeah,
That's
anyway, that's just my
cool.
journey into Swift.
That's cool.
If you're listening to this podcast and you write Swift code and you have any good like Swift resources or Swift tutorials, please just drop a comment, let me know because yeah, like also man, I just totally empathize for people that are getting into like React for the first time because it's just yeah.
Man, I remember when we were running trainings at like EmberConf and stuff, and people were starting, and you're like, they didn't have Node installed, and it was like MP, that could take 45 minutes or an hour or two. I mean, like just your environment. It's when you're in something new like that. It's you're definitely like humbled really quickly.
Yeah, I mean, you can just imagine like it's like, oh, install Node. We recommend using a Node package manager. Here's 3 of them, and you're just,
You're
what
done.
do I do?
But I think you can use React for the actual UI if you wanted to. I don't even know if you need to use React like a web view, but I'm pretty sure that Tuples UI is all React components. I'm pretty sure Dropbox is all React components. I'm pretty sure.
Is
Um,
it React Native?
I think it maybe. I think it might be.
Okay, cool. I have to look
I
into
think
that.
Tuple is web. I'm not sure though. But I know Derek, when he did like the original one, he had a page with all the React components and all the states and stuff, which was a nice way
Very
to
cool.
build it, just
Very
fast.
cool.
Um, and then a menu bar app that I always liked was Contrast from MDS. So you might want to look at that just for some inspiration because it's really good. Um,
Awesome.
I'm guessing he used native because it feels like a native app, but it's like pretty minimal and fast and stuff. So yeah,
Cool.
cool. Today we want to read through this cool queuing article from Sam Rose. My brother shared this with me, so I'm going to go ahead and share my screen here in case you're watching on YouTube, so you'll be able to see it. But we'll read it along so that if you're listening, you'll get the gist of it. But there's a lot of cool like interactive parts of this article. It reminded me of like old Brett Victor articles that I really loved, which are he calls explorable explanations. And I'll put a link to Up and Down the Ladder of Abstraction because that was like the one that this reminded me of right away. And I feel like if you're interested in like teaching and learning and stuff like we are, that's one you got to read. But yeah, we just wanted to read this through, and I wanted to read it with you. I've read it, you haven't read it yet, but
Hmm.
it's about queuing, and it's called the Interactive Study of Queuing Strategies. And I want to read with you because I know that you have a lot of more experience with different backend systems and queues and different parts of server side infrastructure. And I think all this stuff is relevant for that. That's like the most obvious place it is, but it's also interesting, I think, for front end developers. I think it just comes up a lot. It's interesting to think about the web. So, yeah, let's get into it.
Let's
Um,
go.
so Sam talks. He starts off, and yeah, we'll just kick it off here. Queues are everywhere. We queue at bars and restaurants and at the bank. When you loaded this web page, the request to fetch it interacted with dozens of different queues on its way from your machine to the server this page is hosted on. Queues are fundamental. In this post, we're going to explore queuing in the context of HTTP requests. We'll start simple and gradually introduce more complex queues. When you're finished with this post, you will know why queues are useful, 3 different types of queues, how these 3 queues compare to each other, 1 extra queuing strategy you can apply to any type of queue to make sure you don't drop priority requests. Okay, section 1. Why do we need queues? Let's start at the beginning. 1 client and 1 server. For this to work, I'm going to need your help. You're going to play a central role in this post by being the user that sends requests. Okay, so here's our first little interactive bit. It says goals. Click this yellow button to send a request to the server. So if I click that, we see the little dot here moves from the left to the right. In the right, there's this little black box. It's the server. And once you kind of do the goal, you get a little checkbox. So we just sent a request to the server. And then the second goal here is click the yellow button rapidly to see a request get dropped. So he says when you clicked, a request traveled from the button to the server. When the request arrived at the server began processing it. The request shrinks in a clock-like fashion until it has disappeared, at which point it is considered processed. So that's what you see right here. If you click fast enough, you'll notice the server can only process one request at a time, and requests that arrive while the server is busy get dropped. Pretty cool, right?
The amazing.
It's so good. It's so good.
It really is. Yeah, if you're listening to this on the podcast, you got to check out this site because there's so many different ways to explain queues, but this is just the interactivity is awesome. Yeah.
And you can slow down the animations too and speed it up. This is great. Dropped requests are a problem. If these are HTTP requests, dropping them would mean showing an error page to the user. This could cause the user to leave your site, which could be a lost signup or a lost sale. We want to avoid dropping requests if we can. One of the ways we could tackle this problem is to introduce a queue. The next example puts a queue between you and the server. New requests will be temporarily highlighted green to make it easier to see when they end up in the queue. Goals: have 2 requests in the queue at the same time. So now you can see the first request makes it to the server. It takes a second to process. And in the meantime, if I click again, we have a little slot here, and I can just, I can put up to 3 new requests in the slot, and then subsequently they get dropped. So that's what he says right here. When a request arrives at the server and the server is busy, the request is queued. The server takes requests off the queue in the order they were added, processing them at a steady rate. Queues help us smooth the flow of requests to the server. We can't control the rate at which requests arrive, but for the cost of some memory, we can hold on to them until the server is ready. Having users wait a bit longer than usual is often better than showing them an error. You know, whenever we start talking about queues, you always use like the restaurant example, and I think it's good that he mentioned that because that's like the easiest real world example for people to think about. You know, if you came into a restaurant, order a burger, and everyone just gave you your burger, then you could only serve one person at a time, and people now can wait in line. That's like what we're talking about here, and it's first in, first out, right?
Yeah, I think imagine you walk into McDonald's and you're placing an order, and then as you walk in, the person that's working there like goes to the front and flips the "we're open" sign to "we're closed."
Right.
Because you got in line. Then you order, you get your burger, you leave, and then they go back and they flip it to "we're open." So like anyone looking at that would be like, what are you doing? Just leave the store open, have people line up behind the register. So I think that's what this section is highlighting, this idea that if the guy that is working the counter isn't ready to take your order, you just are going to stand in line behind the person that is placing their order. And you won't be dropped. You won't be dropped, right?
You won't be dropped. Yep.
You'll be in the queue.
Yep. And then this would be like the line only supports 3 customers. So after that, you just have to go. You have to leave, something like that.
This is like the New York City bagel shop where, only so many, it can only hold 5 people. And you're like, yeah, I'm not waiting anymore.
Yeah. Perfect. Well said. Well said. Okay. Having users wait a bit longer than usual is often better than showing them an error. So now we have a new section, FIFO, F-I-F-O. The queue we used in the previous example is what's called a first in, first out, or FIFO queue. As the name suggests, requests are processed in the order they were added. So here we see it again. And the goal is to send a request while the queue is full. While queues do help absorb bursts of requests, they can get full. If a request arrives and the queue is full, we still drop the request. Queues do not prevent requests from getting dropped. You might be thinking, why not just make the queue longer? If the queue is longer, it can hold more requests and there's less risk of dropping them. Think back to the bagel store analogy. Well, there's a cost to making a bigger queue, right? The cost is that you have to buy a bigger restaurant or have more space or make a backdoor deal with a local politician and let them wait in line on the city block, which is probably what happened in New York. And the analogy here is that you would need more memory, right? That's part of the cost of adding a larger queue. So let's give that a try. In the next example, the queue size is increased from 3 to 5. The catch is that if a user has to wait more than 5 seconds, they will give up. We'll represent this by making the request hollow. When this happens, we refer to it as the request timing out. So I'm going to fill up the queue here. We have 5 in the queue, and I'm just basically keep on pressing this. And every time the server finishes, and then it takes off the most recent request, it takes another one. So let me just read right here. It says things start off okay, but you'll see that when you fill up the queue, the requests that join in the last 2 slots are at a risk of timing out. When a request gets to the front of the queue after timing out, the server wastes time processing it. So again, if you're listening, I'm pressing this request button a bunch. The server is going through as fast as it can, but eventually it is taking on requests that have timed out. And it still processes them because it doesn't know that the user's gone, but it has gone. So the server wastes time processing it. This then increases the chance that the request behind it will also time out. And you can see that here in the visualization. If you send requests faster than they can be processed, you can end up only serving timed out requests. All of the server's time is spent serving requests that users have given up on. Queue length is an important parameter to get right, and getting it right depends on your application. If in doubt, it's better to be too short than too long. Pretty interesting, right?
Yeah, I've never dealt with this. I've never dealt with a web server that or load balancer that queued up too much, and then the backend servers just got hung up.
Is the timing out because of the backend infra, or is it because of like the client is no longer interested in it, and so you have no way to like move something? It would be like in the bagel store analogy, everyone's in line and they're delivery people, they're bringing it to their person, but it's taking up an hour or 2 hours, and so the restaurant is making bagels for everyone who's in line, first come first serve, but it's taking so long that because the line is long, that by the time the restaurant is making the bagel for that person, they deliver it, the person like already got a pizza from somewhere else. And so the restaurant wasted all their resources getting a bagel for someone where the user no longer cared about the bagel.
Yeah, and even worse in the restaurant case, you're probably gonna have to refund that person. So you
Exactly.
not only delivered them a bagel, but you also refunded them. So you just did a bunch of free work,
Exactly.
while also having a long line and not serving
Exactly.
customers.
Exactly. Exactly.
Yeah. By the way, I think that was my interpretation of this section.
Got
that,
you.
that the client is no longer interested and has left, but whatever. For some reason, the request is still in a queue somewhere.
In a queue somewhere. So when in doubt, it's better to be too short than too long. And then he says, wait, why don't we just drop requests that have timed out? Why are we serving them at all? That's a good question. There's nothing stopping you from devising a system to check if requests are still valid before serving them, but this is not something HTTP servers often do by default.
Interesting. Super interesting.
All right, new section, LIFO. One thing we can do, LIFO. One thing we can do to prevent the problem of only serving timed out requests is to use a last in first out, or LIFO queue, sometimes called a stack. In a LIFO queue, the most recently added request is processed first. This is the opposite of FIFO, where the least recently added request is processed first. So we have another queue here, but when I add a request while the server's busy, it goes to the back of the queue. And if I keep adding requests, you'll see that if the queue is full, we drop it. But as soon as the server opens up again and is free, it takes off, again, the last one, which is the newest request that's been added to the queue. So now it's not timed out. I'll just read this. Processing the most recent request first means it's not possible for us to be in a situation where we only serve timed out requests. However, the mischievous among you may have noticed that it is possible to have a timed out request stuck at the back of the queue indefinitely if you keep clicking the button. And we saw that when I was doing this. For web requests, this failure mode is often preferable. It doesn't matter if the request has been stuck for 20 seconds or 20 minutes, the user is gone. Might as well serve new requests as soon as possible and let the old ones clear out when things calm down.
Interesting. You know, that's funny. My reaction to this is like, stack is a complete wrong data structure for serving web requests. Also, when I watch that visual of you just clicking the button, it's like, whoa, those first 2 requests,
you're just hanging
They're
them
just
and
like
you're
they,
wasting
yeah, they're
memories.
stuck.
Yeah.
Well, also too, it's like no, it's like something inside me. It's like it's not fair. Like,
Right.
why are you giving priority to people that are just coming in? These two requests have been here forever.
Hmm.
But yeah, if they've timed out, if you know your queue in this case is mostly timed out requests, then a stack works better because um, newer requests are less likely to be timed out. So
Hmm.
it's yeah.
It's interesting.
I just had a very like watching that a reaction to how like bad this data structure would be, but it is. I think that last paragraph right there for web requests, this failure mode is often preferable. It doesn't matter if it's been stuck for 20 seconds or 20 minutes. Is I think that's something really good to think about.
Yep, definitely. And it solves the problem from the previous one where we're only serving out
Everything
timed
times,
requests. Yeah,
yeah,
exactly.
everything's timing out. Yep.
Yep.
Guy, could you
Um,
imagine at a bagel store, you're in line and then someone new comes up and the guy's like, I'll take your order. And you're like, I've been here for.
no, but you don't understand. Stacks solve an issue.
Yeah, yeah, exactly. Exactly. Yeah.
All right, priority queues, new section. Both FIFO and LIFO queues treat all requests the same. The only thing that differs is which end of the queue requests get added to. It's not uncommon, though, for some requests to be more important than others. For example, you probably want to make sure a checkout request on your store is treated with the highest priority. To help with this, let's look at priority queues. So this is like Donald Trump that comes to town, and you're like, well, regardless of what you think about Donald Trump, he gets to go to the front of the line. Sorry, too soon. It's 2024. The way priority queues work is that when a new request arrives, it is added to the queue in a position determined by its priority. Requests with a higher priority get added closer to the front. Lower priority requests get added behind higher priority ones. In the following example, we introduce the idea of blue priority requests. These are visually distinct from the yellow requests by color and by the use of stripes. Priority requests jump the queue, getting placed at the front when they arrive. Aren't you just excited to see how the visualization works? This is
Yeah.
so good. So we have a queue here with three. It's three. And if I send the yellow request, it's first in, first out, like before. So I've got a full queue. I'm clicking, and I'm going to click a blue one here. And the blue one jumps the other two. So if I keep clicking the blue one, the blue is always going to jump. And now I have like two timed out requests, normal ones, but there's a spot for the blue one. And you can see we can still drop priority requests if the queue fills up. And it looks like there's only, yeah, but that's the behavior.
Very interesting. You know, I was expecting the priority request to kick
To kick them
items
out.
out of, to kick them out.
Yep.
But that's very cool. But I guess the queue is filled up.
The queue
You know,
filled up.
I've never used this with HTTP requests. But I have used this with like backend job servers. So
Mm-hmm.
oftentimes you'll have something like Sidekick. I use Rails and Sidekick, but any backend job process will, you know, you'll be like sending emails and processing credit card stuff and, you know, whatever.
Summarizing
Everything that,
forms.
yeah, yeah. Anything you don't want to do inside of a HTTP request. And yeah, there's a lot of these systems have like different priority levels because sending someone an email that's like an update that someone replied to your, you know, left a comment on your thing is way less important than like processing a payment. And so, yeah, yeah, that's
So
all.
so when the back end system when the job queue is ready to take off another job, it will look for
It checks
a
a
high
priority
priority.
lane.
Right.
Yeah,
Mm-hmm.
yep, yep. And I
Cool.
think in those, I think the implementation, a lot of the implementation of those is it's like multiple, like you can visualize it as multiple queues. And it's basically, I'm about to process a job. Okay, the first thing I do is I check the priority queue. Oh, it's empty. Okay, I'm going to go back to the default queue.
Cool. All right. Notice that priority requests get added to the front of the queue. This ensures that they are processed first and don't wait as long as low priority requests. When the queue is full, however, we still have to drop priority requests. So maybe that kind of makes sense. Because I remember expecting the same thing. You were expecting the priority one to push out the old ones, but maybe if the job had already started processing an email, and then you push, you know, in the Sidekick example, you push a credit card process. Sidekick's not going to abort or cancel the email job just to free up resources to take off the higher priority job. It's going to wait until it's free again and then start it off again. So I think that's kind of the analogy here, right?
Well, I'm more thinking along the lines of if your queue can only be a fixed size, so it can only hold
Mm-hmm.
3, and you have 3 email jobs in there. By the way, this doesn't translate well to
It
like the
doesn't
back end
translate
job.
because the Sidekick has a database that it uses to store. So that's basically its queue,
Yeah,
right?
and you
And it's
look at
huge.
that as like you think of that as like infinite,
Right.
even though it's not. You think of it
Right.
as infinite.
Right.
Yeah. Anyway, okay, let's go
Yep.
on.
Okay, active queue, new section, active queue management. What we'd like to be able to do is push low priority requests out of the queue to make room when a priority request arrives. This is where active queue management comes in. Okay, so this is exactly what we were just talking about. Up until now, we've only dropped requests that arrive when the queue is full. This is called tail drop because we're dropping the tail end of the queue. This is a simple strategy, but it has some problems. One of the problems is that we drop priority requests. To make it less likely we'll drop priority request, we're going to drop low priority request before the queue gets full. The way we're going to do it is proportional to how full the queue is. If the queue is empty, we never drop. If the queue is 50% full, there's a 50% chance we'll drop. If the queue is 90% full, there's a 90% chance we'll drop. Remember, this rule only applies to low priority requests. Priority requests are never dropped unless the queue is full. All right. So I'm just sending requests, and I had one in the queue, and most of them go through. But when we have 2 in the queue, we start dropping them, just even though there's still room. And what that does is it lets the queue not get full as fast as it otherwise would with normal requests, which keeps the queue more open for the possibility of a priority request coming in. So he says it may take a few goes to see this in action, but you should notice that as the queue gets more full, more requests, more yellow requests, normal ones, get dropped, even though the queue has space in it. Priority requests are only dropped when the queue is full. This is called random early detection, RED, and it's trading off dropping more low priority requests in return for dropping fewer priority requests. Best of all, it's cheap and simple to implement. Because of this, RED is a commonly used AQM algorithm in the wild. I don't know what AQM means. Active queue management. Oh, that's the section we're in. Technically speaking, because we're using different probabilities for low priority and high priority, what we're using here is called weighted random early detection, WRED.
Cool.
Cool,
Yeah,
right?
this is very interesting because there's something here that when you accept a low priority request, you never remove it. So once you accept something, you can say like I've accepted you and you'll eventually be processed, or you don't accept the request, right? Maybe you have room in the queue, but it doesn't accept the request. So there's never like a state where you tell the thing, I've accepted your request. And then later on you say, oh, I kicked you out of the queue because something higher priority. So it's interesting that there's no,
You would think that would
it
be
reduces the state.
possible.
Oh, of course, that would be possible, but I think it introduces more states because
Right,
now you
right,
have a state that is I've accepted you, but then I removed you, but you do not have that state here,
right.
which is interesting, right? It's like
It's a cool way to
yeah,
solve the problem without having to introduce that complexity. And like he said, HTTP servers probably don't do this by default. There's no way, there's no holding place for them. So you just have a server. Given the constraints, you just either have a queue where you can put things to pull them off or drop them. How can you get more of your priority requests through? That's like basic. That's like the constraints of the problem.
yeah,
It's a pretty
and then
interesting solution.
serve like a meaningful error page to the requests that you can't serve. And
Right.
so that way you can actually come back and respond with like, hey, the
Right.
server's busy right now
Right. Right.
because you're
Right.
a low
Right.
priority request and
Yep.
not like, oh, I'm processing you. And then later I just do
Yep.
something,
Yep.
very cool.
Interesting. Very interesting. Okay, cool. Comparing queues, new section. We've spoken about this is really cool. We've spoken about lots of different types of queues. Let's see how they compare to each other. Below, we see all 4 queues we've explored throughout this post. FIFO, LIFO, priority, and priority plus red. Clicking the buttons will, what does red mean again? Random early detection. Clicking the buttons will send requests to all queues. Work through all the goals to generate the data we need for a good comparison. It looks like a lot at first, but I promise it won't take you more than a minute or two. So this is cool. So I'm pressing the request button. We've got the 4 queues, and we can see like the first, third, and fourth, they just push it to the front. And then the second one pushes it to the end. And so let's get 2 in the queue now. So when I do 2 in the queue, the first one is just the normal thing. The second one, LIFO, has a timed out request that's stuck in the queue. The third one, which is priority, is just the normal, because I'm just using normal requests right now. And then the fourth one, we can see if I press this a bunch, it's doing the random detection, and the queue doesn't really ever fill up. So now let's see if I add a priority queue. So the priority queue goes to the front in 2 through 4. And it's kind of cool to just look at the server, look at the black boxes. And if I just press this a bunch, you can kind of see what the server is spending its time on. Mm-hmm. The first one's pretty bad. It looks like it's wasting its time on basically all timed out requests, which we know from the article. The second one is basically just serving the last guy in line. And then the third one, if I have like a bunch of stuff here, the third one gets some priority, but the fourth one definitely gets more priorities done because the queue is not full. That's so interesting, isn't it?
Yeah. Let's
so
keep
cool.
let's keep reading because I think it's going to break down. Yeah, this is what I want to say. Yeah.
Now you've generated a good amount of data. Let's dive into the numbers. All the data below is taken from the request you just sent above. You may also notice the graphs updating as requests get processed. Feel free to send more requests, see how it changes. Wait time. Let's start with arguably the most important metric. How long do requests spend inside of each queue? Below is a bar graph showing latency percentiles for each queue split out by request and priority request. Change the percentile using the toggle below the graph. Does anything stand out to you as you increase the percentile? Remember that 50th percentile is the time at which 50% of the requests are at or below. So if the 50th percentile is 1 second, this means that 50% of the requests are processed in 1 second or less. Okay, so this graph is like a little bar chart. We have the 4 queues, and then I'm at the 50th percentile. For first in, first out, we have 6.6 seconds for both regular and priority. For LIFO, we have 1 second. For priority, we have 1 second for priority requests and 14.3 seconds for regular requests, which makes sense because you're giving priority to the priority request. And then for the randomized early detection, the regular one went up a little bit, and then the normal request came down from 14 to 11.
Let's go the 90th percentile because
90th percentile.
Yeah. So 90th percentile. It's kind of hard to describe these charts, but it looks like they all do a pretty good job processing priority requests, but the default requests take longer and longer.
Mm-hmm. LIFO, they have the longest of 66 seconds, and then the last two are pretty similar.
Cool. Okay, let's
pretty
see.
Interesting, right? At least to me, the standout here is LIFO. At the 50th percentile, it looks to perform well, but gets dramatically worse as you approach the 99th percentile, which is what we saw. This makes sense as it tries to serve the newest request as fast as it can. This gives it a great median at the cost of very poor tail end performance. Dropped requests. Below are a set of bar graphs showing how many dropped requests each queue had, split up by priority and requests. You should notice that priority with red has the fewest drop priority requests, 6 as opposed to 8 for the other 3 with our data set, and the most dropped low priority requests. Yep, that's true. This is the trade-off we make when we use red. All of the other queues should be equal. It isn't a sure thing for priority with red to always have the fewest drop priority requests. It can sometimes have the same as the other queues depending on how you clicked. It will never have more drop priority requests than the other queues, though. That's very interesting. So that's the trade-off that you're making.
Right, because there's like that 50% chance it's going to drop. It might always roll for the never drop.
Right.
But it will never, ever serve more default requests.
Yep. Process timeouts. Lastly, let's look at how many timed out requests were processed by servers. It's a little hard to predict this one because it depends on more how you completed the goals, but you should see that FIFO and LIFO have the most timed out priority requests. Yep, FIFO has 25, LIFO doesn't have any. The priority queues will process priority requests faster and thus have them time out less. You should also see that LIFO has the fewest timed out requests overall. This is again because it prioritizes the newest requests. That's and that we see that in our data too.
Yeah. Wow, this is such a again, it's really hard to describe these charts in podcasts, but this is such an awesome way to visualize to just visualize these queues. Because right at the end of the day, when you're picking between these queues, you're taking some trade-off, right?
Exactly.
And so like you want to be able to just mash that button on this page a lot and then say, okay, which one of these would I prefer? Like
which one fits our business problem, which one fits our use case, and there's not a one size fits all answer. There's not a best answer. I'm sure there's some worse ones, obviously, but none of these are strictly better than the other because if you care more about making sure you don't drop priority requests, you're going to sacrifice dropping normal requests. If you care more about the average time for the 99th percentile, then you are going to be dropping
the 50th. You sacrifice the 50th percentile.
Exactly. Yep.
Also, one thing that's great about this too is it's not writing a bunch of numbers on the screen and saying choose your path. It's more of like a Monte Carlo where you just you just spin the wheel, 500 times, and then you say, okay, which of these would I prefer? So you kind of get there. Yeah,
it's brilliant, isn't it? Awesome.
Yeah,
it's a great way to build up
like
your
this.
intuition. I knew you were going to love this article. I love how it helps you build up the intuition, through the exploration that you do on the page. Let's read the conclusion. I hope you enjoyed this journey through queuing. Let's recap what we learned. There's lots of different types of queues, each with their own set of trade-offs. Queues help absorb bursts of requests, but don't fully prevent requests from being dropped. Priority queues can help ensure important requests are processed first. Active queue management can help process more priority requests by dropping low priority requests before the queue gets full. For HTTP requests, it's common to see FIFO queues used in practice. I would argue, with this post to back me up, that LIFO queues are a better choice for most workloads. If you need to prioritize some requests over others, priority queue with AQM is a good choice, though seen less often in the wild. Queuing is both a wide and deep topic. We've looked at only one use case here, but queues are used everywhere. I hope this post has ignited a desire to learn more about this topic, and if it has, I can recommend the following reads. 2 Weird Things, Observing and Understanding Accept Queues in Linux, Things We Finally Know About Network Queues, SynPack Handling in the Wild, and TCP Global Synchronization. Pretty cool, man.
What a great article and what a great conclusion. Because I think if me coming in cold, who hasn't read this article, if you said I'm building a web server and I'm going to do a stack, a last in, first out queue to handle requests, I would be like, what? No, that's wrong. Like that's wrong. You want a queuing system like you have when you're ordering a bagel at a bagel shop. First in, second in, third in. But yeah, I mean, it's kind of hard to argue with
right.
the results at the end. And again, also too, just like picking your trade-off, right? But yeah, that was just that very, very intuitive answer for me, at least, having the stack, the last in, first out, be like the correct, the takeaway for queuing HTTP requests. Love it.
Yep. Really cool. Really cool. It also made me think back to Ryan Dahls. Is he the Node creator?
Yeah.
His original talk about Node and just what the experiment he wanted to run was, which is that if you have a Rails or PHP server that can only handle one thing at a time, the way you scale it up is by adding more servers. So whereas Node, JavaScript with the event loop basically gives you something like a queue built into the language. And so if you wanted to serve 10,000 requests over some period of time and you would need X number of servers to do that, Node can do it with one server because it has a queue built into it. So it just kind of made me think about that because, this made me think about like long running servers and serverless and how the infrastructure has developed over the last 10 years. And we don't think about this stuff that much at all. I mean, basically, we don't really have to think about it that much. I mean, well, I was trying to remember when the last time this conversation came up when you were talking about the restaurant. We were
It's
talking about like
always
SQLite and yeah, serverless.
and yeah. I will say with like the Node, like Ruby web server requests will queue. It's just that
Mm,
um, I have to like pick my words carefully here. I'm just going to hand wave, but like
yeah,
Ruby traditionally has not blocking IO. So if you can only handle one request at a time and the request is like waiting 3 seconds on a database request to come back, your process is just sitting there waiting on the data. It's not handling the next request. Node's big thing was like this async IO. So you write like you have to use a wait everywhere. And back then we didn't even have a wait. So it was
right.
just it was all callback functions, which was like totally like twisting how you think about code. But anyway, if you have a request come in and it makes a database request or some request to, sorry, you have a request come in and your code is processing that request. And part of the processing that request is you have to go off to a database or an external service. Then your server is just kind of sitting there and waiting for the results from the external service to come back. Node, since it has non-blocking IO, can go off and it can take the next request while it's waiting those 3
Got
seconds.
you.
So it
So
can,
it's not that the Ruby server doesn't have a queue. It doesn't drop requests. It's just blocked and it literally can't do anything. So
it's blocked.
if the first request is it's IO bound, but
Exactly.
there's processing power that's still available there. It's your computer, the web server is not doing anything. It's just literally waiting.
Exactly. Now
Hmm.
I know that Ruby has some non-blocking IO stuff as well, so I don't want to get into
Yeah.
like this language can't do this and this
No,
can't do
it's
this.
more
But
just the
that
original.
was a
That was the
thinking.
original thinking, right?
The thinking of Node is that when you express everything as callbacks, it shapes your program, not just your program, but any libraries you're using,
Right.
anything you're using in a way that like, oh, I'm just waiting for work to come off the event loop, come off that queue. And in the meantime, there's other work that can be done. So yeah.
Yeah. And I thought it was interesting because I mean I remember being pretty like I thought that was very thought provoking, especially because why would he use JavaScript for something like that? Well, it's because JavaScript in the browser has an event loop, and because this is kind of where I think it's interesting how it connects to front end development. What is UI development? You are in a long running UI that needs to stay responsive, even if there are things happening. The user's clicked a button and is waiting. Often our JavaScript apps aren't blocked by they're not CPU bound. You're IO bound in terms of showing the next screen, right? And the way JavaScript is built is so that yeah, you can make the monkey flip, the original Brendan Eich thing. You can click and spin the monkey, but you can still scroll the page. Like that's the whole thing. It's all about that paradigm because it's even though it's single threaded, you have this loop, this event loop that you can push things onto, set timeouts, set intervals, set asynchronous functions, and so there's just an interesting connection here. That's like I think a lot of front end developers will understand that part of it.
Yeah.
Cool, good stuff. Pretty interesting, right?
Yeah, great article.
Yep. Um, cool. I think we should wrap this there. Maybe there'll be some follow up stuff. I feel like it'd be interesting to talk more about long running servers and serverless and if that affects like how that affects app developers. I don't know because I mean this is like details of a web server that we never think about, but I just find it interesting that again in the last year or two, um, whether you're using serverless or a long running server does leak into your app architecture in a very big way, and it affects a lot of things for app developers. So I don't know if there's any what the overlap there is with the queue discussion or not, or if it's just a completely separate conversation. But it made me think about it anyway. So
Yeah, I think there probably is. Like, I think um, you're 100% right that I would say the serverless stuff does leak into your architecture where you aren't thinking about like every HTTP server I use might be using this
right.
LIFO queuing strategy, but I never ever think about it. So yeah, that's
I guess the only way that this leaks in is more of a just an understanding that when you are making a website, you have to be cognizant that the fact that there's kind of an implicit contract that web requests should be about, whatever, 250 milliseconds, a couple seconds. If you have a long
Yeah.
task, you need to put it in a background job. This has come up with our AI consulting stuff a little bit as well, and people using AI to just like, you can imagine if you had a web server that used one of these queues, and instead of this server taking 1 second to process it, it's like a stream from Chat GPT, and it's just, you can see that would wreak havoc on your server. So anyways, just something else to think
Yeah.
about. But
It is funny that that is like a really good use case for the serverless stuff, is
mm-hmm.
because you want to just spin up a whole new. I like thinking of it as like train stations, right? Like
Yep.
you have a bunch of trains coming in. Serverless, you get to build a new train station for every single request that comes in.
Yes.
But generally with like really fast HTTP requests, we don't really think about it that much. But yeah, ChatGPT now takes 5 seconds to respond.
You can just
And
look at this graph.
it's
You would just, if the black thing was taking 5 or
yeah,
10 or 15 seconds, you're just done. You're smoked. This whole architecture doesn't work anymore.
yeah, yep. Very interesting.
Cool. Awesome. All right. Fun article. Definitely link that in the show notes. You should take a look for sure. Sam Rose was the author. He has a lot of cool stuff on his website, so check him out as well. And yeah, if you have any questions, hit us up. Comments on our YouTube video. We look at those. And we're at Front and First FM on Twitter. So yeah, that's it for this week. Thanks for listening, and we'll see you next week.
See ya.
Bye.